This video is about section 8.3 notes, testing a claim about a mean. So for our example, it says a sample of 106 body temperatures has a mean of 98.20 degrees Fahrenheit and a standard deviation of 0.62 degrees Fahrenheit. Use a 0.05 significance level to test the claim that the mean body temperature of the population is 98.6 degrees Fahrenheit, as is commonly believed. So identify the claim to be tested, and you'll notice this is exactly the same process that we used in section 8.2, just with a few differences. So I'll be pointing those out as we go. So the claim to be tested is that the mean body temperature of the population is 98.6 degrees Fahrenheit. So mu, the mean of the population, is exactly equal to 98.6 degrees Fahrenheit. The opposite of that, so if the original claim is false, or the exact opposite of this would be that mu is not equal to 98.6. And then for our null and alternate hypothesis, our null hypothesis is always going to be the symbolic form that had the equal sign. So mu is exactly 98.6. And the alternate hypothesis is the other one. So mu does not equal 98.6. And then the significance level, it was 0.05 significance level, so alpha is 0.05. Okay, step 5 is to identify the statistic from the sample, which was the mean. And here, if we remember our chart from step 5, we had two different categories where we could find the mean from, depending on whether or not we had the population standard deviation, and typically the population standard deviation is not known. So we will often not be doing this. We will usually be doing this situation right here. So through the rest of the notes, I'm going to get rid of this row completely, because if we're not usually going to be doing it, then we shouldn't spend time learning it. So typically we're going to be doing this situation because we will not know what the population standard deviation is. All right, and we're going to be using a t distribution, because our test statistic that we're using is t. All right, now because we used a does not equal symbol, we're going to be doing a two-tailed test for this problem. Okay, so we need to find several things. So if we look at this formula, we need x bar and mu. We also need the sample standard deviation as well as the sample size. And then because we're using a t distribution, we're going to need the degrees of freedom. So x bar in the problem was 98.20, mu was 98.6, and the standard deviation was 0.62. So those are all degrees Fahrenheit. In the problem, it said that it was 106 body temperatures in the sample, so sample size is 106. Degrees of freedom is 105. All right, so I'm going to go ahead and calculate my t value. I have x bar minus mu, 98.20 minus 98.6, divided by s over square root n, 0.62 over square root 106. Oops, put my decimal in the wrong place on the bottom. There we go, 0.62. Okay, So negative 6.64. I'll do 4 decimal places just in case. I think these they want more answers on MyMathLab. Okay, so we know from our t-chart that we're dealing with a distribution that looks like this, and in this case I have 2 tails, and so I'm going to go ahead and draw a situation that looks like this. This is what I have, so let me go ahead and draw that. So remember, you can decide to reject the null hypothesis or fail to reject the null hypothesis based on the critical value, based on what you find from the distribution table. So I'm going to find the critical value based on the significance level using my t-distribution table. Now, my degree of freedom was 105, but 100 is all I'm going to be able to find on the table, so this is what I'm going to have to work with. The area in 2 tails that I'm working with, or the significance level, is 0.05. So I'm working with area in 2 tails. I'm looking at 0.05, and I'm going all the way down to 100, and I get 1.984. So that's going to be my critical t-value, and it's going to go for each of the 2 tails, 1.984, negative 1.984, and I'm going to label that on both sides. Okay, so if I found that these are my rejection regions right here, if I have a t-value that's greater than 1.984 or a t-value that's less than negative 1.984, then I need to reject the null. Then I just got a value that's at negative 6.64. That is definitely in this region over here, and it's in the rejection region. So if I'm using a critical value, I have already decided that I can reject the null hypothesis. However, I'm always going to teach you both methods because we know that one method is from the critical values, the other method is from the p-values. So what I want to do next is I want to find the probability that the t-value is less than negative 6.6423. And when we were doing this in the last, when we were doing this in the last set of notes, we were able to take the z-score for proportion, and we were able to find it on the chart, and we were able to get an exact p-value. And what's different about section 8.3, and then again will be different as well about section 8.4, is that we are not going to be able to find the exact p-value. You have to use technology to do that, and we're not going to. We're going to find approximate p-values. We're going to find a range of p-values. So I'm going to look for the p-value over here, where the t is less than negative 6.6423. And what you'll notice just looking at your entire t distribution is that none of these t values are negative. They're all positive. So the t values, they're not talking about this left side of the picture over here. They're not talking about negative critical t values. They're always mentioning positive critical t values. So we're basically going to use the absolute value of the t value that we're talking about. So I know that my t value is negative 6.6423, but I'm going to think of it as positive 6.6423. So what I want to do now is I'm going to look at my degrees of freedom, my 100, and I want to figure out where along this row that t value of 6.64 would fit. So I have 1.290, 1.660, 1.984, 2.364, 2.626. A t value of 6 would definitely be right here. So 6.64 has to fall right here. And then I'm going to go up and I'm going to approximate where I think my p-value is. So if I go all the way up here, I can see that my p-value is going to fall down here wherever this is. So this is a p-value of 0.20, 0.10, 0.05, 0.02, 0.01. My p-value is less than 0.01, but I don't know exactly what it is. Okay, so my p-value is less than 0.01. Okay, I'm going to say my p-value is less than 0.01. I'm not sure exactly what it is, but it's less than 0.01. Okay, now I need to make the decision to reject the null hypothesis or fail to reject it. I already said from the critical values, I can see that this critical value is in the rejection region, but I can also see that my p-value is less than my significance level. So I have a p-value which is less than 0.01. I don't know what it is, but I know it's less than 0.01. And 0.01 is less than 0.05, which was my alpha. And so this means that my p-value is less than my alpha. And if the p is low, the null must go. And so that means that I need to reject the null hypothesis. Okay, my next step, step 8, is to go through and restate the decision using simple and non-technical terms. So, does the original claim contain the condition of equality? Identify the claim to be tested. Here we had mu is 98.6. That was the original claim. It had equality. And so here we're going to say yes, the original claim contains equality. All right, then step 2 says, do you fail to reject the null or do you reject the null? We reject the null. And so this is how we're going to start our sentence. We're going to say there is sufficient evidence to warrant rejection of. There is sufficient evidence. There we go. To warrant rejection of the claim that the mean body temperature of the human population is 98.6 degrees Fahrenheit. All right, let's try the next example. So this one says, an airport tracked 48 departure delay times. Negative values correspond to a flight that departed early. The mean for the flights was 10.5 minutes and the standard deviation was 30.8 minutes. Use a 0.01 significance level to test the claim that the mean departure delay time for all flights is less than 12 minutes. So the mean is less than 12 minutes is the claim to be tested. The exact opposite of this is greater than or equal to 12 minutes. The null hypothesis is always the equal to version, but only using an equal sign. So mu is equal to 12 minutes. And then the alternative hypothesis is always the other version. So mu, let me label what I'm doing. Mu is less than 12. Okay, and then the significance level was 0.01. And then because of how this is phrased, because it says mu is less than 12, this is a one-tail test, not a two-tail test. So we know this is a one-tail test. The test statistic we're going to work with, we're going to do a t-distribution, and we're going to find the t-value. I know that because in this context, when we're dealing with mean, that's pretty much what we're always going to be doing. But I also know because the problem said nothing about a standard deviation for the population. It only had S, which is a standard deviation for the sample. Okay, so that's how I know that I'm using this one and not the other row that was in the table that I've now deleted. Okay, so let's go through. I wrote the example problem again at the top of the page in case you need to reference it. So it says find the value of the test statistic, and honestly it probably would have been good if I had written the formula as well. I'm going to go ahead and write it now. So T is x bar minus mu over S divided by square root n. Okay, so we need x bar, we need mu, we need S and n, and we need the degrees of freedom since we're using a T distribution. So x bar is 10.5, mu is 12, the standard deviation is 30.8, the sample size is 48, and the degrees of freedom is 47. So our T value is x bar minus mu divided by the standard deviation over the square root of the sample size. And so let's figure out what that is. Negative 0.3374. Okay, and so now I'm going to work with my T distribution, and my T distribution always kind of looks like this, so that's the picture that I'm going to draw. And this time I have a one-tailed test, not a two-tailed test. And my null hypothesis was that mu was less than 12. And so I'm going to be looking for less than. I'm looking at the left tail. And I need to figure out what this critical value is. So my degree of freedom was 47. 47 is not on the table, but 45 is. So I'm going to go ahead and use 45. My alpha value was 0.01. So I'm going to use 45. I'm going to use the area, and one tail is 0.01. So I'm going to go 0.01 all the way down to 45. And my critical value is 2.412. If this was on the right side, I would make that positive, but it's on the left side, so I'm going to make it negative. Negative 2.412. And then I'm going to think about where this number shows up. Does it show up in the rejection region, or does it show up over here in these acceptable values? So negative 0.33, if it's less than negative 2.4, it would be in the rejection region. If it's greater than negative 2.4, it would not be in the rejection region. And this number is going to be somewhere over here. It's not showing up in the rejection region, which means I'm about to fail to reject the null hypothesis. But I'm going to go ahead and I'm going to do the p-value as well. So this is using critical values to make my conclusion, but you can also use the p-value. So the probability that t is less than negative 0.3374, I'm going to grab this. I'm going to look at my degree of freedom, and I'm going to look and see where the positive version or the absolute value of 0.3374 shows up. So I've got larger values this time, so 0.3374. 0.3374 definitely shows up over here. 0.3374 shows up over here. And we're looking for the one tail, not the two tail. We're looking for the one tail. And so I'm going to go up here and I'm going to look at the values, but I'm not looking for two tails. I'm looking for one. So the area in one tail, we had 0.005, 0.01, 0.025, 0.05, and 0.10. I don't know what it is because it's over here. I know that that number was smaller, but I do know that the area in one tail is getting bigger as I move this direction. So that I know that the area that I have has to be bigger than 0.10, but I don't know exactly what it is. So I know that the probability that t is less than negative 0.3374 is greater than 0.10, even though I don't know what that probability is. So my p-value is greater than 0.10. And for me to reject the null hypothesis, this number has to be less than my significance level, which is 0.01, and that's just not the case. This 0.10 is greater than 0.01, and so I fail to reject the null hypothesis. Fail to reject the null hypothesis. Okay, so if I look back up here, remember there are two ways I can do this. One is I can draw the distribution, label the t-value based on my alpha, based on my significance level, and then determine if the t-value that I calculated is in the rejection region or not. The other way is to calculate my p-value in this case for section 8.3, and then again in the next section, we're not going to be able to find an exact value, we're just going to find approximately where it is. And based off of approximately where this is, 0.10 is definitely greater than 0.01, and so we fail to reject the null hypothesis. Okay, so now we're going to look at this. Does the original claim contain the condition of equality? The answer is no. The original claim was that mu was less than 12. Do you reject the null hypothesis? And the answer was no. We failed to reject the null hypothesis. And so we're going to write the sentence this way. We're going to say there is not sufficient evidence to support the claim that the mean departure delay time that's the R, departure for all flights is less than 12 minutes. All right, and we have one last example to do. This example says, listed below are the ages of randomly selected race car drivers. Use a 0.05 significance level to test the claim that the mean age of all race car drivers is greater than 30 years. So the claim to be tested is that mu is greater than 30. The opposite of that is that mu is less than or equal to 30. And so for the null and alternative hypothesis, we know that the null is always the claim that would include the equal sign, so mu equals 30, but it is only the equal sign. Mu equals 30, and then the alternative hypothesis is whatever the other one is. So the alternative hypothesis is that mu is greater than 30. Identify the significance level. Alpha is 0.05. And then we know that we're going to be using the t-value. And so now we can go through and find these values. And we're going to have to actually calculate some of these because instead of giving us these values, they gave us a sample. So I'm going to go ahead and fill out what I can, and then I'm going to use my calculator to get the rest. So we know that mu is 30. We don't know x bar, the mean. We don't know s, the standard deviation. We're going to have to use our calculator for those. We know the sample size is 3 times 5. There's 15 numbers here, so we know the sample size is 15. We know the degree of freedom is 14. Okay. So let me go ahead and get this all plugged into my calculator. I'm just going to clear my memory. So if I hit stat and edit, I can type these all in. 32, 29, 27, 32, 38, 45, 33, 32, 52, 33, 33, 29, 41, 23, 25. And then if I hit the stat button again, and it's not saying I have 16, it's saying the next number would be 16. So I only have 15 numbers. If I hit the stat button again, I can go over to calculate, and I can calculate one variable statistics. And just press enter. So X bar is 33.6. And S is 7.6699. I'm just going to do 7.67. Actually, let me go ahead and do more digits there. Usually if you're going to be working with any numbers, the more digits that you have when you write a number down are better, so that you do not make any rounding errors. It's better to round more at the end of the problem. So I'm going to write 7.66. See, 99, that's going to have to round all these numbers up. So I'm just going to write 5 digits. I'm going to do 66998. 66998, so that I don't have to round as much. Okay. So our t value is going to be x bar minus mu over the standard deviation divided by the square root of the sample size. .8178. Okay, and I'm going to go ahead and draw my t distribution. And I didn't say this yet, but let's look back at the... Oh. Don't have to look back at the previous page because it's right up here. Mu is greater than 30, so since it's greater than, that means that this is a one-tailed test, and it means that it's the right tail, not the left tail. So when it was less than, it was a one-tailed test, but it was the left tail. When it's greater than, it's a one-tailed test, but it's the right tail. So this is my rejection region over here, and I'm going to go ahead and use my t distribution to find the critical value that's going to help me define that rejection region. So I'm looking for a degree of freedom of 14, and I'm looking for an alpha value of 0.05. So area in one tail is 0.05. Rejection region is 14. And so I have 1.761. 1.761. And this number right here is to the right of 1.761. And so it actually does fall into that rejection region. So I already know that I'm going to have to reject this number. But let me go ahead and find my p-value. So I'm going to find the probability that t is greater than 1.8178. And so I'm going to grab my table again, and I'm going to look and see if I can figure out where 1.8178 would fall. So I'm looking at my degrees of freedom here. 1.8178 would fall in between these two. 1.8178 is between these two, and now I'm going to see what that value is so I can figure out my p-value. So I'm going to go up. I'm not stopping here because this is the area between two tails, or not between, but the area in two tails. I'm going to go up here. So my p-value is between 0.025 and 0.05. 0.025 and 0.05. I don't know what it is, but I know it's between those two values. So I'm going to say the p-value is between 0.025 and 0.05. And as long as the p-value is between this, that means that the p-value has to be smaller than 0.05. That was our alpha value. So this means p is less than 0.05, and so p is less than alpha. So here we saw that we need to reject the null hypothesis because the t-value we found is in our is in our rejection region. And we did this based off the critical values. But here we found approximately where the p-value would be. And when we found approximately where it would be, we found that the p-value was less than our significance level. And we know if the p is low, the null must go. So this tells us to reject the null hypothesis. Okay, so to write our sentence, does the original claim contain the condition of equality? The original claim was that mu was greater than 30, so it does not. Do we reject or fail to reject? We reject. And so we're going to write our sentence saying there is sufficient evidence to support the claim that the mean age of all race car drivers is greater than 30 years.